I've published this video as both Pure 2 and Additional Maths, so it'll be a little bit more challenging for the grade 10 Additional Maths course. For our first part here, we have to write the expression, the following expression that you see, in a certain form. So we have to rearrange for our third part there. So we need the same base. So we're going to do the change of base law and then do a rearrangement. And there's two little parts here I'm changing. So change of base in general, and then the power law, we're going to put that exponent of 1/2 out front. So simplifying things down, that's what we're always doing with these questions. So that's isolated out on the right hand side. Now we'll actually begin our question. So we have our log to the base a of 9 plus a log to the base a of b, and our part that we just completed there. From that part, actually, there's a few more little pieces I need to do. So I have like log to the base a 9 times a. So you need to be careful here. The multiplication rule, we're going to get log a to the base a to a. And of course, to the base a of a is 1. So we'll do that in a second. And of course, on the denominator there, we have 1/2 to the log to the base a of b as well. Our log to the a of b, there's two of them. There's one on the top and one on the bottom. We can cancel them out. So there's two little things I'm doing at once there. I've denoted it with color if you need a little extra visual. So just rewriting all of that now and taking out what I've just said. And of course our log to the a of 9 plus 1 is divided by 1/2 now. So just multiply that second part by 2. So we'll have a log to the base a of 9 plus 2 log a to the base a of 9 plus 2. And of course that's just rewritten whatever order you want, but 2 plus 3 to the log to the base a of 9. That's our first example. There are quite a few little things to change, a few rearrangements, the change of base law, a few little laws in terms of the logarithms. So be very careful with them. Next question up, simultaneous equations. Can be difficult to look at. Well, you need to take logs. That's basically the rule there. So taking logs of that, we'll end up with x plus 2y is equal to log 5. Our first one. And the second one, 3x plus 4y is equal to log 50. So when we're doing simultaneous equations, we want to get one of our unknown values the same. So we can add or subtract. So the first equation I'm going to multiply by 2. So the y values are both 4y. So same sign, subtract, you'll end up with x is equal to log 50 minus 2 log 5. Now, our 2 log 5, we're using a power law again. You'll end up with log 5 to the power of 2. I'm just going to do that on the other side of the board. So log 5 squared is 25. So again, log 50 minus log 25. Remember your division rule. So 50 divided by 25 is log 2. From there, I think we can just substitute in. So we had x plus 2y equals log 5. So x is log 2. So log 2 plus 2y is equal to log 5. And from there, we can get y. So 2y is equal to log 5 over 2. And so y is equal to 1/2 log 5 over 2. And x was log 2. So there are two values in exact simplified form. Okay, last question, third question, moving on. So we have two equations and we need to show something. Okay. First one, so log to the base 2, y plus 1. I'm going to just rearrange it there, of course. And again, you can use your power law there as well. So the 2 out the front in the second term. We'll make it log to the base 2. X squared is equal to 3. And from there again, you're adding them, so multiplication law. So log to the base 2, y plus 1 in brackets and x squared in brackets equals 3. And just take logs, so y plus 1 times x squared is equal to 2 cubed, which is 8. That's our first equation rearranged. The second one, again, rearrange it. Get the logs on one side. So we have a division law here, so log to the base 2, x plus 2 over y is equal to 2. And from there, again, take the base out of it, so take logs. X plus 2 over y is equal to 4, so y is equal to x plus 2 over 4 when you simplify it down. And from there, basically, as usual, you kind of just have to substitute in something. So we're going to use that y value there in our first part that we have there. So y plus 1 in the brackets times x squared, we're going to replace the y there from the left-hand side. And from now, we're going to expand brackets. So x plus 2 times x squared, that kind of thing. We end up with x plus 2 times x squared all over 4 plus an isolated x squared, because x squared times 1 is x squared, is equal to the 8. And from there, you can multiply across 4 by everything. Multiply the brackets first as well, of course. So you end up with x cubed plus 2x squared over the 4, and then plus x squared equals 8. So get rid of that 4 by multiplying on both sides. So you'll have x cubed plus 2x squared plus 4x equals 32, and put those two middle parts together, x cubed plus 6x squared minus 32. And that's the answer for that. We've just shown what was asked. Find the roots. So a little bit of trial and error actually with this kind of question when you're finding roots for cubics. You can guess it's like 0. Well, you want to get the answer to be 0. So you generally just test it with 1, minus 1. In this case, I just did it with 2. So 2 cubed plus 6 times 2 squared minus 32 is in fact a factor, equals 0. The factor theorem there. And now we're going to test a remainder theorem or whatever. We're going to do some synthetic division now. X minus 2 divided into x cubed plus 6x squared. There's no x coefficient, so put that in as 0x minus 32. And just start doing the synthetic division there. So we have x times x squared is x cubed. Remember to subtract there. So 6 minus 2 is 8. And if we put it for 8x, and then you'll have 8x minus 16. So our last part is plus 16. And you'll bring down your 32, it'll be the same thing. So 16x minus 32, and of course there'll be no remainder. Just multiply the 2 that you see there as well. So that's that last part. And so we'll end up with a factor of 2, which is great. And as you can see, probably you could do this in your head. But 16, so 4 times 4. So we have a minus 4 repeated root for that as well, for the cubics. And there are the roots. So it's 2, a minus 4, and another minus 4. You have a reason why only one of these roots is valid. So hopefully this is straightforward. You can plug it in. Of course, you need to prove it. So we'll just take any of our equations or partial equations that we had already. So log to the base 2, x plus 2. Plug in that, you'll get minus 4 plus 2, which is, in fact, log to the base 2 minus 2. We can't have negative solutions. So x is equal to 2 is the only real root. And we're going to also find our y. So the value of y corresponding to that, log to the base 2, so y plus 1, we're going to plug it into that equation. So the first one actually, so just rewrite that, minus 2 log to the base 2. So again, if you've log to the base a by a, it's 1. So in this case, we have at the end there log to the base 2 of x, which is 2. So to the base 2 of 2 is 1. So 3 minus 2 is 1. So we're just going to write that out now. So log to the base 2, y plus 1 is equal to 1. And then taking log, so you'll have y plus 1 is equal to 2 to the power of 1. And finally, y equals 1. So our values there were 2 for the x and 1 for y. And that's the end of our questions on logarithms for pure 2 or we'll say challenging questions for additional maths as well.